Hi all, I'm Saket Gurukar. I'm going to present the multi-biasage work in this video. Now we know that networks are present everywhere. Examples include social networks, biological networks, road networks, and many others. This ubiquitous nature of networks is because networks provides a general language for describing and modeling complex systems. Now, there are several interesting machine learning tasks which we can perform on networks. For instance, we could perform node classification, where we could classify a node into one of predetermined classes. Another machine learning task on networks is link prediction, where we could predict if a link exists between two nodes or not. Now, an interesting application of link prediction based machine learning algorithm in a real world setting is Pinsage. Pinsage learns pin embeddings from a large pinboard graph, where the pinboard graph consists of more than 2 billion pins, 2 billion boards, and contains more than 7 billion pinboard edges. Now, given the size of the graph, Pinsage employs a scalable random walk strategy to identify the neighbors. These neighbors would then be utilized in the computation graph of graph neural network to compute the pin embeddings. The Pinsage model is then trained on its application-specific loss function. Now, pin embedding is at the core of machine learning models used at Pinterest, and it's widely used in most of the systems, such as related pins recommendation, user modeling, and email notification system. Hence, the quality of pin embedding is extremely important for Pinterest, as improving the quality of pin embedding would in turn improve the performance of systems that rely on pin embedding. Now, the current version of Pinsage, however, only relies on pinboard graph to learn the embeddings. But at Pinterest, they have multiple entities such as users, ads, products, and search queries. And there exist diverse interactions among these entities, such as a user can buy a product at Pinterest, or a user can click on an ad, or a user can enter a search query, observe the search results, and then click on one of the search results. In this work, we hypothesize that these diverse interactions contains valuable information and can be utilized to learn even better quality pin embeddings. To that end, we model these diverse interactions using heterogeneous graphs. Here, the diverse entities are represented through nodes of a particular node type, and diverse interactions are represented through a particular edge type. However, the current Pinsage system is not designed for heterogeneous graphs and cannot learn the pin embeddings from the heterogeneous graph. So a straightforward approach would be to utilize existing heterogeneous graph models to learn pin embeddings. Now, there exist several heterogeneous graph models, such as heterogeneous graph transformer, heterogeneous graph attention network, and heterogeneous graph neural network. However, it is difficult to train these models on Pinterest heterogeneous graph. The first challenge is the scale of the graph. Note that the recommendation system has to operate on web scale, and these existing models assume that one can load the graph and node features into memory. However, loading these graph and node features require more than 3 dB of RAM, which is not always feasible. More than the memory constraint, the problem is of compute constraint. Again, note that we are operating on billion node graph. To give an idea of how time consuming the training is, we can do the following thought experiment, where if we assume that we can sample the node neighbors, perform message passing, compute gradient, and update the node embedding in 1 millisecond, then it would still require 55 days to compute node embeddings for all the nodes in one epoch on a single system. So training heterogeneous graph model on Pinterest scale data on a single system machine is not feasible. Now, a few distributed heterogeneous graph models exist. For instance, Amazon has released this digital framework while Alibaba has proposed AliGraph. These frameworks have three common layers, often have three common layers: storage, sampling, and operation layers. However, each of these layers make certain assumptions or have requirements that are not easy to fulfill. For instance, to store the graph and its features, these frameworks first partition the graph using existing graph partitioning algorithms. So given a heterogeneous graph, these frameworks assume that the given graph is a homogeneous graph and apply existing graph partitioning algorithms developed for a homogeneous graph. Now, this graph partitioning creates two problems. The first problem is it's extremely difficult to perform long random walks for nodes that lie on the periphery of the partition graph. And the second problem is that the graph partitioning algorithms often rely on heuristics such as edge cuts and vertex cuts to identify the communities. The underlying assumption in these algorithms is that there exist few number of tightly knit communities and the network follows a power law degree distribution. However, when operating on a billion scale heterogeneous graph, we don't know if these assumptions hold or not. The storage layer also addresses the problem of storing and retrieving node features. This aspect is also important because, as mentioned earlier, storing node features requires more than few TB of space, which is not always feasible. So to solve this problem, these frameworks either partition the node feature matrix or store the feature matrix in a key value store. However, both these approaches require an API call for retrieving the node features, and hence rendering the approach bit time consuming. The next layer is sampling layer, where these frameworks provide multiprocessing support for sampling node neighbors, while the operation layers incorporate graph neural network operations such as aggregation and combination. Where both these layers require large number of workers, typically in the order of thousands, and employing these large number of workers is costly. Hence, to train a heterogeneous graph model on Pinterest scale graph, we propose multi-bisect work. Multi-bisect consists of 4 steps. In the first step, we decompose a heterogeneous graph into multiple bipartite graphs. Next, we run random walks on each bipartite graph and collect intermediate information. In the third step, we collect ground truth pairs for training. And in the last step, we train a novel model that aggregates the intermediate information to learn deep embedding. We'll take a look at each of these steps in detail. In the first step, we decompose a heterogeneous graph into multiple bipartite graphs. The stats of the curated bipartite graphs are shown in the table. The nomenclature for the graph name is entity 1, entity 2, and edge type. Here, pinboard graph is still the largest graph and is followed by the search query pin long click graph. Note that these graph contains diverse entities and their diverse interactions. Additionally, a disclaimer that these graphs represent a random subset of entities present at Pinterest. Next, we run random walks on each bipartite graphs. Here we use in-house random walk system called Pixie that loads the complete graph into 2 TB RAM machine. The random walk system consists of highly optimized C++ routines that can perform multiple random walks from each node. Now, in the figure, we show a candidate pin and its neighbors identified by Pixie from different graphs. We observe that the candidate pin neighbors from diverse graphs seems to follow a non-similar data distribution. For instance, if we look at pinboard neighbors, they seem to have similar style and color, while the neighbors from search query pin graph have different style and colors. We believe that these diverse signals helps us in building better recommendation systems. Note that in our model, the node's features are identified before model training, and we don't sample new node neighbors over each epoch. The next step is collection of ground truth. Here, when the user clicks on a pin, say query pin, that user is shown multiple recommendations. So if the user clicks on the pin from this shown list, we call that interacted pin as engaged pin. We basically treat the query pin and engaged pin as positive training example, and we randomly sample few million pins and treat them as negative pins. Next, we collect the visual and textual features of query and engaged pins. The visual features are computed through a large-scale transformer-based pre-training on Pinterest images, while the textual features are computed using multitask training. We also collect these features from pin neighbors collected in step 2. The last step is training the model that learns the pin embeddings. Here, for each bipartite graph, we take the pin's visual and textual features and that pin neighbor's visual and textual features and first pass it through feed-forward network. Here we have feed-forward network specific to each type of features. We then pass the output of the feed-forward network to bipartite graph-specific transformer. The graph-specific transformer outputs graph-specific pin embeddings. So for k bipartite graphs, we have k pin embeddings, which are again aggregated with another transformer to learn the final pin embedding. And we train multi-bias model with sampled softmax loss. So the viewer is suggested to look at the paper for more details about this loss function. Now, I would like to point out a few important observations. First, we played with different model architectures, but the model performed better when we assigned different parameters for each bipartite graphs. This observation is in line with the designs of other models such as RGCN and heterogeneous graph transform. Those model too assign different parameters for each node and edge type. Second, we observed that a vanilla transformer is inefficient with respect to multi-bias edge. In vanilla transformer model, we can form a single sequence where the sequence consists of the pin and all of its neighbors from all the bipartite graphs. Then we can pass the sequence through the transformer to learn the pin embedding. However, this approach increases the sequence length by k times. And this is problematic because the time and the memory complexity of transformer is quadratic with respect to the sequence length. So as a result, a simple transformer model requires more memory and takes more time to train as compared to the multi-bias model. Next, we compare our proposed model against the deployed version of Pinsage on recall at 10 metric. At Pinterest, they have multiple surfaces where the main homepage is called organic surface, and there are pages dedicated to ads, products, idea, and video pins. A user can have different interactions with these entities or surfaces. From the table, we see that multi-bias consistently outperforms Pinsage on all the surface and achieve the highest improvement in ads, idea, and video pin surfaces. Next, we look at the kind of recommendations given by Pinsage and multi-bias model. Here we first learn that we first learn the pin, query pin and engage pin embedding, and also learn the pin embeddings of 1 million random pins. For the query pin, we compute its similarity with the engage pin and 1 million pins based on their embeddings. We then rank the pins depending on the similarity scores and then show the top 5 similar pins. Here we see that the query pin is children's cycle. The engage pin's rank for Pinsage is 364. Hence, we have 0 recall at 10 score. While for multi-bias edge, the engage pin rank is 5. So we have a positive recall at 10 score. And we also observe that all of the recommendations, except one given by multi-bias edge, seems reasonable. We would also like to note that multi-bias edge is not specific to Pinterest and is generalizable to other data sets. Finally, I would like you to take away 3 main points from this talk. First is that it's extremely difficult to train heterogeneous models on large-scale data. Second, multi-bias provides an elegant solution for training these graph-based heterogeneous models. And third, multi-bias is generalizable and can be applied to public data sets. Thank you.